I did a little experiment and I want to go over all the details of the calculations. There's two calculations really. The second one's the most important, how to do stuff in Python. So here's the experiment. I put this scale in an elevator, and then I put an aluminum block on the scale, and then I pressed a button on the elevator, not saying which way I went, and then I looked at the reading on the scale. So I'll just start with the first part. See, it's 102 grams right there, but then when I push a button, it goes up to something like 109 or whatever. Let's just wait till it goes up. And then from that, I also have the time that it was higher reading, the time that it was back to normal reading, and then a time when it went back down. And what I want to do is to find the height of the elevator. Okay, so I'm going to do this the very, very rough way, a rough calculation, and then we're going to do it with Python with the very much better detail data, and that's what the fun part. Okay, but I want to start off with the overhead, the rough view first. Okay. It's pretty good. It's pretty fun. I was surprised it turned out that well. Honestly, I'll be surprised. So here's my scale, and there's my block. When the elevator is accelerating up, then I have the two forces acting on the block are the normal force, I'll just call that N, and the gravitational force, mg. But in the y direction, F net y is going to be N minus mg, and that's mass times acceleration. Now, the normal force is the reading from the scale. And so if the scale reads 109 grams, it's kind of like that's m times g, another m. So I can write this as m2, the scale reading when it's accelerating, times g minus the normal reading times g equals the normal reading times a. And if I solve that for a, I get a is g times m2 minus m over m. So I can calculate the acceleration. Now, it's not constant. Okay, I've approximated it as constant. So it's not constant, but I can calculate this as g times 109 minus 102 over 102. And I don't even have to worry about converting those to units of kilograms because that's grams, and the grams cancel. So I just get units of g, which would be meters per second squared. That works. Okay, so if I do that, let's put that in my calculator right here. Oops, I'm sorry, what was that noise? Okay, calculator, drop. So I have g as 9.8, and then I have that 7 times 102 divided by, and I get 0.675 meters per second squared. So that's the acceleration that is moving up. Now, I looked at the video, and very, very roughly, I got an acceleration of 1.5 seconds, and then it went to a constant speed for about 5 seconds. This is not the best way to do it. But what I can do is to use this time to find the velocity during that phase. And then for the velocity, I can calculate how far it went. I'm going to ignore the distance it traveled during the acceleration phase. I'm going to ignore the distance it traveled during the slowing down phase because it's just a rough approximation anyway. Okay, so let's do that. And it'll give us a place to start, and then like I said, we can get a much better value. So let's find the velocity. So in the y direction, I can say A is the change in velocity with respect to time, v2 minus v1 over delta t. And then I know my initial velocity is 0, and my delta t is 1.5 seconds. I know my acceleration. So v2 is v1 plus a delta t. So it's 0.6. What did I just erased it? Got it right here. 672 times 1.5. So my velocity, my travel velocity, which is just approximation, is 1.5 times that. So I get 1.0 meters per second. Now, for the second phase, it is moving at a constant velocity. So I can say the velocity is the change in y with respect to time. And I want to solve for how far it went. Delta y is just going to be v delta t. So it's going to be 1 times 5, or 5 meters. And it's not 5 meters. It's actually closer to 4. But it's not terrible, right? It's not 100 meters. It didn't go crazy out of control like that. So it's a very good rough approximation. I'm pretty happy with it. It's not perfect, but it's good enough. Now, if you want a better way to measure the acceleration, you can. And I used the PhyPhox app, which you should have the PhyPhox app on your phone. It's a free app that allows you to collect data from your sensors. So I put the phone on the floor, I pressed record, and then I pressed acceleration record, and then I pressed the elevator button. And let me show you what that looks like. I can't show you my phone because I'm using my phone to record this video, surprisingly. Okay. So here is a screenshot from that phone. So this shows you the acceleration in the X, Y, and Z direction. So if you have your phone like this, the face is in the Z direction. So towards the screen, perpendicular to the screen, is the Z direction. So this is the X acceleration. I'm not even sure which, I assume that's left to right. And you'll see that it's very, very small just due to shaking of the elevator. And the same thing for the Y acceleration this way. There's just one little bitty kick right there. I can mostly ignore those, even though I can't. I see that right now. And I'm gonna address that problem, and we can talk about it later. But here's the one that I want to look at. So there's my acceleration during the speed up, constant speed, and then slow down. And I can export this data as a spreadsheet and send it to my computer, which I already did. Okay, and so I have this in Google Sheets, and there's a lot of tedious stuff that I'm going to do, but I'm going to show you all the steps because you might want to do it too. And I do things my own tedious way, you do things your tedious way, and there's no right way. Okay, so here's the sheet. What I did actually, I just went from about 12 seconds here to 24 seconds because there's a lot of just nothing happening. And I have this spreadsheet. So here's my data. And so you'll see that it has the time, the acceleration, the x-axis, y-axis, z-axis. I'm just going to use the z-axis, but I think that you could use other directions too, because I made the assumption that my phone was completely flat, and I think because of the camera, it actually tilts up a little bit. If you want to play with that, you can. I'm not going to play with that right here. Okay. So the first thing that I want to do, that you'll notice that it has an acceleration in the z direction of 9.73, 9.72, and all that. So that's because of Einstein's equivalence principle, which says that the acceleration is the same as the gravitational field, so it can't tell the difference. But I need to subtract that off from my data, and that's the first thing I want to do. So let's just do that. I'm going to say 9.72. So over here, I'm going to make a new column because that's. No, I'll do it in Python. I want to get this data into Python first. Okay, so what I'm going to do is I'm going to get the time data. I want to list it as put it as a list in Python. And there's a lot of data here. And this is a terrible idea, but I'm doing it anyway. Let's put this in here, and then I'll talk about the calculation. So I'm just going to copy this column. I'm just going to see if I do that. Copy. Now, if I paste it into Python, it won't look right. Okay, because I need to put commas between all the things, and I could have saved it as a comma separated value and everything, but I didn't. Okay, so I'm going to go over here to text edit, and I already have it. I already tried it to make sure I had it right, and I'm going to paste that value in here, and you see it's this big old stuff. It's all that data, and I want to come up here and delete the time. I don't want that. I don't want that first row. Now I'm going to I already find the return value and replace it with a comma, and then I can replace all. And there, what a mess. But now I copy that. Let's go to Python now. So here I am in Python, and I'm just going to put my data. So I'm going to call this T, and it's a list. Make that a little bit bigger. It's a list. So I'm going to put my square brackets. I'm just going to paste that in there, and it's one ginormously long line. But it's there, and we can do this. Print. That's still not big enough. What happened? Why is this so small? You know, like, that's better. Print the length of that list just to see if it's working. And I get, see, it is pretty long, 1,238. Now let's get the acceleration. I'm going to do the exact same thing for the acceleration. Where did that go? Here it is. So I'm going to go over here. I'm going to use the Z acceleration. I'm going to click this and copy the whole column. Go over here to text edit. I'm going to delete that stuff, paste this. I'm going to get rid of that first row because it had the Z. I don't want that. I'm going to get rid of that, and then I'm going to replace all. And then I'm going to copy it, select all, copy all, and then go back over to Python right here. And I'm going to call this the A list. Paste that. And then let's print that. Print length of A. Because if they're not the same length, I'm going to have a problem. Okay, good. Now, what do I need to do next? I have to do a bunch of stuff. First, I need to change my A values by subtracting 9.72. And then I need to find, so let's do that. So I'm going to go through each item in the list A and subtract off that value. So I can do that for I in range A, length of A. And this will go through each element and call the number I. And then I can use that to index the thing A. So I'm going to say A index I is equal to A index I minus 9.73. And let's just see if it works by printing A0. Let's run that. Okay, so it's almost 0. That's exactly what we want. Okay, so we have our time data, we have our acceleration data. The first thing I want to do is to just plot the acceleration. I want to just plot the acceleration, and then we'll talk about how to find the velocity. Because I want to make 3 graphs. I want to make an acceleration graph, velocity graph, position graph. So over here, let's make a graph. G1 equals graph. Let's give it a title. Accelerating elevator. That looks cool. Let's give it a X. I'm not going to give it an X title. It's going to be in time, but I'm not going to. I will. X title equals time in seconds, and then Y title equals AZ in meters per second squared. And then I need to do this. Width, no, you got to spell it right. Width equals 400. Height equals, let's put it at 150. I want to make it kind of skinny. Now I need a graph to plot in there. I'll call this F1, G curve, color equals color.blue. I don't need to print that. I don't need to print that. I do need that. I don't need to print that. Okay, so now let's just go through the whole thing again. I know we don't actually have to do another for loop. I'm going to. For I in range, length of t. Let's do t, because that's really the one that we want to plot. I'm going to plot the t value and the a value. So f1.plot ti, ai. And let's see if this works. I didn't even save it. There you go. So it does look like the data from PhyPhox. That's pretty good. And you want to check that, right? You don't want to just plow forward and not even know if what you're plotting is or dealing with is real stuff. Let's save this. Elevator analysis. Save. Okay, now let's jump to the board. And how would I find the acceleration? Because if you've done numerical calculations before, where you calculate the force and use that to calculate the acceleration and use that to update the velocity, that's the same thing we're doing right here, right? It's just that we already have all the accelerations. We don't have to calculate them. Why didn't it save? I asked it nicely. Let's see, it says entitled. Something weird happened. Okay, it did it. It's just slow as slowness. Come on. Okay, well, I'm going to hope that loads. Let's switch over to the computer, the board, and talk about how we're going to calculate the velocity, because I want to make a velocity time graph. And now we're dealing with one dimension, so we don't have to worry about that. Oh, it came up. Yay. Okay. So in one dimension, I can say the acceleration is the change in velocity with respect to time. So if I want to imagine that I have data like this, acceleration versus time. So here's my acceleration data. There's a data point, data point, data point, data point, data point. Okay. How do I find the velocity for these data points? Well, what I can do, and this is not right, okay, because really what we're doing is integrating the whole function. I can say the velocity at that point is equal to the velocity before. Actually, I'm going to start right here. It's going to be the velocity before, which is going to be v0, plus a delta t. So if I know this time interval, which I'm going to need to calculate that, I'm going to take my first velocity, which I need to know. The acceleration does not tell me the velocity, it tells me the change in velocity. I'm going to use this. Does it matter which one I use? No. I can use either one of these accelerations, multiply by delta t, and add it to the original velocity to get the final velocity. So I need this delta t, and then I need to make a v list so that I can add stuff to it. Okay, so that's what we're going to do. It's going to be great. Switching back to the computer now that it loaded. Okay, don't know why it's so slow. Let's go ahead and make our v list. So I'm going to call it v, and it's a list with just 0 in there because I want to, I need an initial velocity to start with, so 0 is my initial velocity. Now I can go through and calculate, I need dt too. dt is going to be t1 minus t0. Now I could just look and determine what that should be, but I'm just going to take the second element in my time list minus my first, and if I'm assuming they're all the same time intervals. I'm pretty sure there are. I didn't actually check though. But why wouldn't they be, right? I think it's 100 data points per second. Now I can do this for I in range length of t minus 1. So since I already have the first v, I don't want to go through all of the a, and I'm already using that a thing, right? So I don't want to, if I do range of t, I'm going to end up with one extra velocity. I don't want to do that. So I'm going to calculate my velocity. Let's call it vn for my new velocity. It's my old velocity, which is going to be vi, right? Because it's going to start at 0, plus ai times dt. So that just calculates the velocity. Now I need to add it to the list. So v equals v plus vn as a list item. And that should do it. And then I'm going to go through and plot. Let's just do this right down here. Let's plot them all together. Oh, I didn't make a graph. So let's make another graph. So in Web v Python, if I make a new graph, g2 equals, I'm going to copy that, because I don't want to type it. G2 equals graph. I'm going to get rid of the title, because there's only one at the top. And this is going to be equal to v in meters per second. And then also I'm going to get rid of the title down here, the x title, just because it runs into my other one and I don't need it. And that's fine. And then I'm going to say f2 is g-curve color equals color.red. So in Web v Python, when you make multiple graphs, if I make a graph and then a function to plot g-curve and then another graph, it will automatically associate it with the one right above it. You can explicitly state that, but we don't have to, so that should be fine. Down here, I'm just going to plot f2.plot ti vi. And let's see if this thing works, because you never know, it might not work. But it worked, and that's just beautiful. That is really great, right? Because look how nice that looks. This does show that it looks like it's moving down at the beginning, which I'm not really sure about that. And then it increases in speed up to a constant velocity and then starts moving down. It may be something with my sensor too. I haven't played with that. But you'll notice that everything's lined up perfectly. Love it. You can see that right here is where the acceleration starts, and it's lined up right there. I mean, come on. Textbook awesome. It's textbook awesome. You will also notice right here that my velocity, I'm getting about 0.44 meters per second. So I calculated 1, but again, I assumed this acceleration was much higher for a constant period, but it decreases right down there. So there's that. Now, we just need to do the same thing with position. And I'm not even going to write it on the board, because we know what to do, right? I can do the exact same calculation with position, but I need to make a position graph, and I need to make a position function, a list. So let's just do that. I'm so excited. It looks awesome. Okay, so down here, I'm just going to copy this whole thing and paste it right here, and then change this to 3, and this will be my position graph. So it's going to be meters. This is y. And then I need to change the, and I'm going to take off the x title there, right? because they're butted up next to each other, so we don't need those extra tiles. You can put it there if you want to. You do it the way you like to do it. And then this is F3. I don't actually have to have a different color, but I'm going to make it purple because that's what I want to do. And you do it the way you like to do. Now down here, I'm going to make, should I do it all in the same? Let's just do another list. So let's say y equals 0. So I'm starting at y is equal to 0. And then I'm going to do very similar thing. For I in range, length of t minus 1. Yn, the temporary y, is the old y, yi, plus vi times dt. And then I'm going to add that to my list. Y equals y plus yn. And then down here, I'm going to plot it. F3.plot ti yi. Let's see what that looks like. Okay, there's my acceleration, there's my velocity, and there's my position. And that's, come on, that looks really great. It looks really great. So, but this says that I went a height of, let's say, 3.17 meters. I measured it and I got something closer to 4. I think there's something weird about my data. I really haven't explored it yet, but I want to redo this. But I had the data, and it doesn't really matter. The analysis is the same no matter which, even if your data is bad, right? So we can get the height here. And you'll notice, this is what I'm talking about, getting rid of that x-axis. It makes these next to each other a lot better, and it looks awesome. I think it's pretty cool. So there's that. Okay, there you go. That's how you take the data from the PhyPhox and you plug it into Python and use it. Oh wait, these aren't lined up anymore. I see that because of the axis right there. There's a way you could probably fix that, but I'm not going to. It's still pretty cool. Okay, that's that. The end. Talk to you later.